Imagine a single chain link weighing 500 pounds and almost 4 feet long. Now, hundreds of such links connected together, stretching for 1,000 feet and weighing tens of tons. This isn't a movie set for a film about titans. This is the anchor chain of a supertanker, capable of holding a vessel the size of a skyscraper in a stormy sea. These giants of marine engineering don't work in the quiet of a harbor, but in the harshest conditions on the planet, under insane weight, with temperature fluctuations from -40 degrees Fahrenheit to positive 120 degrees, in salt water that eats away even the strongest steel. The first and most important step in producing anchor chains is choosing the right steel. For chains that must withstand tremendous tension in the open sea, low alloy structural steel with increased strength, impact resistance, and corrosion resistance is used. Its composition is selected so that the chain doesn't break from metal fatigue, isn't eaten away by salt, and doesn't crack from temperature fluctuations. Factories receive steel in the form of solid rods or square bars, which look like long metal beams. Their diameter usually ranges from 3 to 6 inches, and their length up to 10 feet. The weight of one such piece is hundreds of pounds. All of this is stored in open assembly yards or inside large metal hangars, because the parts can withstand any weather conditions. Before being fed into production, the steel is checked for purity of composition. Even minor impurities can make the metal brittle. After quality inspection, the steel heads to the cutting lines. These are long automated sections, where massive rods are transformed into blanks for links. Each steel rod is picked up by a hydraulic manipulator and placed on a guide. Then, the main hero of this stage comes into play: a hydraulic guillotine press, or a cutting saw with carbide discs. The device calibrates the length, and when the blank is in the correct position, it presses with a force of thousands of pounds per square inch. With each loud thud, a characteristic crunch is heard, and a piece about 3 feet long is separated from the rod. This piece will become one link of the future anchor chain. A counter is displayed on a special screen or directly on the machine's body. It tracks how many links have already been prepared and whether the length needs to be adjusted. Each cut piece falls onto a conveyor or into a basket, where it is automatically checked by a laser scanner. If the system detects a deviation in length or an uneven end, that piece is sent back for remelting or trimming. The pieces that pass inspection are moved on to heating furnaces, where a bright orange heat of over 2,000 degrees Fahrenheit awaits them. This temperature allows the steel to soften without losing its structural properties. It is there that the steel will become pliable and ready for bending into links. The cut pieces of steel, incredibly thick, rough, and heavy, are still cold, so they can't be bent at all. To give them the shape of a link, they need to be made pliable. The blanks are fed onto a roller line that leads directly into an induction or gas furnace. Inside the furnace, a dull hum can be heard, and the air is heavy, hot, and saturated with a metallic smell. The blanks lie on stands or are suspended on special rods and are gradually heated for 20 or 30 minutes. Externally, they begin to glow, first cherry red, then orange, and finally almost white. This is a visual indicator. The steel piece is ready for forming. As soon as the piece reaches the required temperature, it is quickly removed by a robot or a worker in a heat-resistant suit, because there's no time to waste. Steel loses heat very quickly, and if it cools by even 200 or 300 degrees, it will no longer be bendable. That's why the logistics of the hot chain production are so well coordinated. Every second matters. As soon as the 2,000 degree Fahrenheit blank is removed from the furnace, it is instantly transferred to a bending machine, which looks like a hydraulic press robot with metal arms. These units can easily manipulate pieces weighing several hundred pounds, rotating, securing, and bending them with surgical precision. The essence of the process is simple at first glance. The blank is clamped between two massive forming rollers, one of which rotates around an axis. At the same time, the other presses with a force measured in tens of thousands of pounds per square inch. The steel yields and smoothly bends, forming a perfect ring with a diameter of up to 4 feet. While the metal is still soft, the ends of the link are joined, leaving the joint area slightly overlapped. Then the link is transferred to a welding station, where gas-shielded arc welding automatically begins. The temperature, over 5,000 degrees. The electric arc literally melts the edges and stitches them into one hole. The finished link is almost a part of the anchor chain, but before it is connected to others, the seam must be ground, heat-treated, and checked for defects. And only after this does it become part of a chain capable of holding a supertanker weighing hundreds of thousands of tons in a rough sea. While the link is still hot and pliable, it is immediately connected to the previous one, threaded through the already finished link. Only after this is the link closed, the seam welded, and this entire dual unit undergoes further processing. After all, it's impossible to open the previous link without damage, which would affect the chain's strength. When a link is welded, a noticeable seam remains at the joint, a bit rough, with weld spatter and metal buildups. In this state, it won't pass any tests, as it could catch on other links or even become a weak point under pressure. So, grinding comes into play. On a huge table, similar to a workbench for airplanes, lies a link weighing under 300 pounds. It is secured so that the seam is clearly accessible. An abrasive machine or an operator with a powerful grinding tool gets to work, which roars, sparks, and makes a characteristic buzz sound. The goal is to smooth the seam as much as possible, remove micro cracks and excess metal without damaging the main structure. Grinding takes place in several stages: first coarse, then medium, and finally, polishing. For this, discs of different grits are used, from 24 to 120, and sometimes even higher. After grinding, the link is blown with compressed air, cleaned of dust, and at this stage, it already looks like a perfect ring. But an external shine is not yet a guarantee of strength. So next comes heat treatment. Heat treatment strengthens the metal structure and makes the chain capable of withstanding insane loads in the depths of the sea. This is a complex series of thermal processes that are carefully controlled. First, the links are heated in furnaces to a temperature of 1,700 degrees Fahrenheit. Huge chambers, resembling metallurgical tunnels, hold dozens of links at once. Here, it is important to achieve uniform heating throughout the thickness of the metal, so that no internal stresses arise that could cause micro cracks. Next comes quenching. The links are rapidly cooled, usually in baths of oil, water, or a special salt solution. It is this temperature jump, from red hot to cold, that creates a hardened crystal structure in the steel. The result is increased hardness and wear resistance. But after quenching, the metal becomes too brittle. So the next stage is tempering. The links are placed back in the furnace, but at lower temperatures, approximately 1,000 degrees Fahrenheit, and held there for several hours. This allows residual stresses to be relieved, restoring elasticity and a balance between hardness and strength. Sometimes induction hardening is used, where heating occurs locally, only in the areas that experience the greatest loads. For example, the inner surfaces of the link where it connects with others. After heat treatment, the links are coated with an anti-corrosion layer that protects the metal from salt water, moisture, and rust. This is usually a hot dip galvanized coating, or epoxy paints, applied by dipping or spraying. Before this, the surface is degreased and ground again. The coating must lie evenly on every indentation, because the durability and safety of the entire structure depend on this. Imagine taking the air you are breathing right now and turning it into a substance that can freeze ice cream in 3 seconds and make a banana tough enough to hammer nails. This is not magic. It is liquid nitrogen. Every second, it is used in medicine, science, the food industry, and in some top-secret experiments. Temperature, -321 degrees Fahrenheit. One sip, and you lose part of your stomach. One breath, and you unlock tomorrow's technology. How does the coldest substance on Earth get made from regular air? How is it transported, stored, and used? And why can it save or destroy? Watch closely and prepare to be amazed. It all begins with air. Yes, the very same atmospheric air that surrounds us. This happens inside industrial air separation units. These systems come in all sizes, from massive factory installations to mobile units for medical use. Air is sucked in using compressors. Then it passes through filters. First, coarse filters that remove dust, insects, and pollen. Next, fine filters get rid of moisture, carbon dioxide, and other impurities. Once cleaned, the air is compressed using powerful machines, increasing both pressure and temperature. Then, it is gradually cooled in heat exchangers. When the high-pressure cooled air moves through a narrow nozzle into a low-pressure chamber, it expands rapidly. That sudden expansion causes a major drop in temperature. This is the key moment. The gas becomes cold enough to start condensing into a liquid. This process repeats several times. Each cycle drops the temperature further. Eventually, nitrogen reaches its liquefaction point. This technique does not work with every gas, but it is perfect for nitrogen. Thanks to this, we can create liquid nitrogen from ordinary air. Once the air is chilled and liquefied, it goes through fractional distillation. This process separates the liquid mixture into components based on their boiling points. Inside a special distillation column, the liquid air is gently reheated. Nitrogen has the lowest boiling point, around -320 degrees, so it evaporates first and rises to the top. Oxygen boils at -297 degrees, so it evaporates later and does not climb as high. Argon, with a boiling point around -302, settles somewhere in between. The column forms a thermal gradient, colder at the top, warmer at the bottom. The gases evaporate and condense over and over, becoming purer with each cycle. It all works without additives, automatically, and with minimal losses, thanks to precisely managed pressure and temperature. Since nitrogen makes up roughly 78% of air, extracting it takes powerful equipment, a complex network of pipelines, and exact temperature control. Once separated, liquid nitrogen is stored in special vessels, cryostats, or Dewar flasks, which look like futuristic thermoses. These vessels keep temperatures low and prevent evaporation. They are not just metal barrels. They have double walls with a vacuum in between to block heat. Some also include reflective coatings to minimize radiant heat loss. These containers can preserve liquid nitrogen for several days to several weeks, depending on volume, insulation, and how often they are opened. Often, nitrogen is used right on site. For example, medical facilities use liquid nitrogen for cryopreservation of cells, embryos, vaccines, and tissues. In the food industry, it is used for flash freezing. Contact with liquid nitrogen instantly freezes food, locking in texture, taste, and shape. But when it needs to be transported, preventing evaporation is critical. That is because nitrogen quickly turns back into a gas. Portable dewars, cryotanks, and cryotank trucks are used. Small dewars are handy for labs and clinics. Cryotanks are massive, like giant gas tankers, and are hauled by trucks with special mountings and ventilation. Cryotank trucks are purpose-built vehicles with insulation and pressure regulation to avoid explosions from expanding gas. Sometimes, liquid nitrogen is produced directly on site, at large research centers or hospitals, to avoid reliance on deliveries. How did humanity tame one of the coldest, most inert substances on Earth? It all began with nitrogen. Discovered in the year 1772 by Scottish chemist Daniel Rutherford, who was studying air and found a gas that could not sustain fire or life. That was nitrogen, colorless, odorless, inert. But liquefying it required cold and pressure, and humanity needed more than 100 years to figure that out. The first liquid nitrogen was produced in 1883 by Polish scientists Zygmunt Wroblewski and Karol Olszewski. They built a system that cooled air so much that nitrogen, its main component, turned into a liquid. That was a breakthrough. In the 20th century, cooling tech advanced fast. Scientists improved gas liquefaction methods and eventually developed the Joule-Thomson cycle, which relies on pressure drops to efficiently liquefy gases. In the 1930s and 50s, liquid nitrogen made its way into industry and medicine, starting in labs, then into surgeries, biobanking, and physics experiments needing ultra-low temperatures. Today, liquid nitrogen production is a global-scale operation. It is made in massive air separation plants around the world. What was once just background gas, making up almost 80% of air, has become a superstar of industrial science. Some chefs even make ice cream live, pouring cream into a bowl, adding liquid nitrogen, mixing, and voila, instant dessert. The cold is so intense, it freezes the treat in seconds. Dip a banana in liquid nitrogen for a few seconds, and you can hammer nails with it. Seriously. Want to try? Inhaling cold nitrogen vapor can temporarily change your voice, like helium, but deeper. But do not try this. It is dangerous without protection and special equipment. Some people have dipped old socks into dewars of liquid nitrogen. Result? The fabric becomes brittle like glass and crumbles in your hands. A perfect way to destroy evidence. If you are a sock. Pour liquid nitrogen on a warm floor, and it turns into a dramatic cloud. It vaporizes instantly, making you feel like you are stepping through a Hollywood portal. What should you never do with liquid nitrogen? Even if it looks cool, never stick your hand into it. Online videos show people dipping fingers and pulling them out unharmed. That is the Leidenfrost effect. A brief protective vapor layer forms around the skin, but if you hesitate for a second too long, hello frostbite, do not try it. Seriously. Never drink it. Yes, that happened too. In several restaurants, smoky desserts were served with a drop of liquid nitrogen. One careless guest sipped before it had fully evaporated and lost part of their stomach, literally. Afterward, several countries banned such stunts. Do not pour it on your bathroom floor. The vapor looks cool, sure, but tiles can crack from thermal shock. Plus, the risk of suffocation in a small space is real. Nitrogen displaces oxygen. Do not pour it in the toilet. Not because it will definitely break, but it might. And because pipes can burst. Some TikTokers have proudly frozen their plumbing. Utility crews must love them. If you are not an engineer or a molecular gastronomy chef, do not try freezing food or fruit from the inside. Liquid nitrogen can rupture the skin and explode in your hands, especially with high moisture items. So yes, liquid nitrogen is amazing, but it is also incredibly dangerous. Respect the frost. Every year, the world produces over 10,000 tons of titanium discs, the material used to create the hearts of airplanes, implants for surgeries, and even parts for spacecraft. A single disc can weigh more than a smart car, but it fears neither temperatures of 1,800 degrees Fahrenheit nor the vacuum of space. How does a gleaming superdisk, capable of withstanding thousands of revolutions per minute, emerge from a gray, spongy mass? What do aviation, medicine, and the titanium hell of furnaces have in common? This isn't just manufacturing. It's a show of strength, precision, and engineering magic. Let's dive into a world where metal takes on its perfect form. Titanium discs are blanks shaped like thick discs made from titanium or its alloys. They serve as the starting material for parts in highly critical fields: aviation, medicine, space, energy, and automotive manufacturing. Titanium is a true superhero among metals. It's lightweight yet extremely strong, withstands insane temperatures, resists corrosion, and doesn't react with the human body. That's why it's used for everything, from aircraft components to implants. But pure titanium is a bit finicky. It's difficult to machine and can be brittle under certain conditions. Therefore, it's often mixed with other elements, creating alloys. The most popular alloy consists of titanium with 6% aluminum and 4% vanadium. It's strong, wear-resistant, and easier to form. Aluminum adds lightness and heat resistance, while vanadium adds flexibility. For medical devices, pure titanium or alloys without toxic elements are used. Depending on the task, titanium can be harder, more ductile, or more resistant to extreme conditions. That's why manufacturers choose not just titanium, but the specific alloy that perfectly meets the particular challenge. Titanium for discs comes from titanium sponge, the primary raw material extracted from ores, mainly ilmenite and rutile. The largest deposits of these ores are found in Australia, South Africa, China, Kazakhstan, and Canada. But the sponge itself is produced where complex manufacturing facilities exist because the process of converting ore into metal is very energy intensive. It all begins with a dirty grey, pumice-like substance, titanium sponge. It arrives at the plant in large containers and bears almost no resemblance to the future aerodynamic part. But this is where the journey starts, ending with the gleam of a perfectly polished disc capable of withstanding thousands of revolutions per minute. First, it's checked for impurities and moisture. Acids or solutions that react with impurities are used, removing them from the titanium surface. This process might involve treating the raw material in special baths. Titanium parts might also undergo abrasive treatment, such as grinding or sandblasting, to remove surface contaminants. After cleaning, the titanium raw material undergoes heat treatment to improve its structure. The raw material is heated to a specific temperature, usually between 1,300 and 1,600 degrees Fahrenheit, and held there for a defined period. This helps reduce internal stresses that might have occurred during previous processing stages. If necessary, the raw material can be heated to higher temperatures to achieve homogeneity in the alloy structure. This ensures an even distribution of elements within the material, enhancing its strength. After heat treatment, the titanium undergoes a fascinating rapid cooling stage, which is quite a spectacle. When the metal is removed from the furnace, it glows with bright shades of red and orange, reflecting the high temperature it was heated to. Cooling can be done in several ways, by quenching in water or by air cooling. When submerged in water, you can observe the hot titanium creating foam and bubbles as it rapidly contacts the liquid, emitting a characteristic crackling sound. This is visually impressive, as the boiling water witnesses an incredible transformation, from a potentially malleable state to a strong metal. Alternatively, air cooling is calmer, but no less captivating. The metal gradually loses heat, changing its color and texture. This process, although less dramatic, demonstrates the smoothness and elegance of titanium's transition to its final form. Then, the material is loaded into special crushers or hammer mills. The main purpose of crushing is to reduce the particle size of the titanium, facilitating further processing and ensuring material uniformity. The crushed particles can be used in various processes, such as producing powder alloys or forming new parts. After crushing, the resulting particles may be washed to remove residual debris or impurities. They are then dried in preparation for further processing. To manufacture the titanium discs themselves, the blanks are heated to high temperatures, typically up to 1,500 or even 1,800 degrees Fahrenheit. This is done to make the titanium softer and easier to work with. The heated blank is placed in a press or hammer. Impact action or pressure shapes the blank into the desired disc form. During this process, the titanium undergoes significant deformation, leading to changes in its structure. For casting, however, special molds are made, usually from steel or cast iron. The molds must be very precise to ensure the correct geometry of the disc. The titanium is heated until it turns into a liquid. This is usually done in vacuum furnaces to prevent oxidation. The liquid titanium is poured into the prepared mold. After cooling, it solidifies, taking the shape of the disc. Casting allows for the production of discs with complex shapes that are difficult to achieve by forging. Now it's time for machining. Before machining, the discs are cleaned of dirt and residues. For this, they are immersed in a special bath with a solution that removes slag and grime. The water foams up, and the disc becomes clean. Next, the discs are secured on lathes for stability during machining. A lathe is used to remove material from the edges of the disc, achieving the required diameter. Thin metal shavings curl away from the cutting tool like a slender snake. The contours and profiles of the disc are formed according to technical specifications. If grooves or holes are needed, a milling machine is used. Then, the discs are processed by grinding machines to achieve the smoothest possible surface. This is important for reducing friction. Finally, they are polished to obtain a shiny surface, which also enhances their aesthetic qualities. Polishing can further protect the disc from corrosion. After polishing, the surface becomes smooth, reducing the likelihood of dirt and moisture accumulation. Fewer imperfections and cracks mean fewer chances for corrosion. Polishing also seals microscopic pores that can retain moisture and contaminants. This significantly reduces the risk of oxidation. Afterward, the disc is inspected for scratches, cracks, or other visible defects. Calipers and micrometers are used for precise measurements of the disc's diameter and thickness. To detect internal defects not visible on the surface, ultrasonic testing is performed. This inspection method does not require direct contact with the disc. A special transducer emits ultrasonic waves into the disc material. As the waves travel through the disc, they reflect off boundaries such as defects or the material itself. The time it takes for the waves to return to the transducer is measured. This allows for the detection and sizing of defects. Specialized software analyzes the received data, providing information about the disc's condition. This is a very fast process, allowing many discs to be checked quickly. Titanium is 40 times lighter than steel, but has comparable strength, making it ideal for the aviation and automotive industries. It does not rust or corrode in most environments, making it a durable choice for various applications. In the United States, an average of 10,000 to 15,000 tons of titanium is produced annually. A significant portion of this amount is used for manufacturing discs and other components. Thus, on a monthly basis, this could amount to 800 to 1,200 tons of titanium discs. Leading companies in the United States, such as Boeing and Lockheed Martin, actively invest in the production of titanium discs to meet the needs of their programs. It is expected that in the coming years, the demand for titanium discs for aviation will grow by 5 to 7% annually, especially considering new technologies and increased aircraft production. As of the year 2025, approximately 135 million monitors are shipped to markets worldwide every year. This includes both new models and replacements for old ones, as part of a typical 4 to 5 year tech upgrade cycle. While it is difficult to pinpoint the exact number of monitors in global use, due to varying lifespans and growing demand, it is estimated to be in the billions. That is because as much as 66% of the global population uses computers. But what happens when it is time to recycle a monitor? Cathode ray tube monitors, those old bulky screens, were common before flat screens took over. They contain glass with high lead content, phosphors, and electronic components. Lead in the glass can make up as much as 20% of a monitor's weight. Sounds dangerous, right? Light-emitting diode, or LED monitors, are the modern flat screens that use LEDs for backlighting. They are lighter and more energy efficient, but still contain plastic, metal, and rare earth elements. Guess what? Mishandling these monitors can cause serious environmental problems. Lead from CRTs can leak into soil and water, and plastic from LEDs can take centuries to decompose. That is why recycling is not just a trend, it is a must. In the United States, over 4,400 million pounds of e-waste is generated every year, but only 25% is recycled locally. Every single day, Americans throw away more than 500,000 computers and mobile devices. This creates a massive environmental challenge. Electronic recycling centers, like Repowered in Minnesota, play a key role in addressing this issue. Each year, they process about 3 million pounds of electronics, which makes up 5% of all electronic waste collected in the state. Impressive, right? These centers accept any device with a cord, except for large appliances, and ensure proper disposal or reuse. Some states, like California, go even further. There, it is illegal to dispose of e-waste in regular landfills. California has over 600 drop-off locations, and recycling is funded through a fee on the sale of new monitors and televisions. By the way, California spans around 163,696 square miles. It is the third largest state. Trucks are loaded with old monitors and driven to recycling centers. This method is typically used for short and medium distances. For long hauls, container shipping is used. It is more cost-effective and safer for large volumes of electronics. At the plant, monitors are unloaded in the intake area, where trained staff inspect them for hazardous materials and evaluate their condition. The monitors are disassembled into key components, such as cathode ray tubes, display panels, power supplies, and other electronics. This process can be done manually or with specialized equipment. The separated parts are sorted by material type. Casings, power supplies, and other metal components are separated for further recycling. Recycling metal parts from monitors looks like a full-on industrial operation. Massive machines work in sync to turn scrap metal into something new. Shredders roar. Furnaces blaze. The air is thick with the scent of molten metal and the noise of industry. Metal components are cleaned of contaminants like paint, plastic, and other non-metallic materials. This is done with machines that strip away surface layers and boost metal quality. Rotating brush systems or dedicated surface cleaning machines are used. This step can also involve shredding, crushing, or other mechanical methods. Metals might also be treated with chemical solutions to remove corrosion and other residues, using acids or alkaline solutions to dissolve unwanted layers. Then, the metal is shredded into smaller pieces using large presses or industrial shredders. This makes it easier to process and transport. Next, metals are sorted by type. Ferrous metals are separated from non-ferrous ones. Each metal type requires a different recycling process. The metal pieces are then melted down in giant furnaces at high temperatures. Steel melts at about 2,552 degrees Fahrenheit, while aluminum melts at around 1,112 degrees Fahrenheit. As the metal melts, impurities are removed and the material is poured into molds to form new ingots. These ingots are used to manufacture new metal products like construction materials, car parts, or home appliances. Using recycled metals cuts production costs and preserves natural resources. At smelting plants, huge conveyor lines move metal pieces through different recycling stages. Workers in full protective gear oversee the process to ensure safety and quality. Thanks to this effort, old monitors are reborn as new, useful products, helping the environment and advancing sustainability. Plastic components from monitors and other electronics are collected and sorted by type, usually polycarbonate, acrylic, and polystyrene. They are shredded into small pieces using machines like industrial shredders or crushers. This makes the plastic easier to transport and process. The shredded plastic is then cleaned to remove contaminants and impurities. This step uses air jets, magnets, or other tools, depending on the plastic type. The clean, shredded plastic is melted and molded into pellets. These pellets become the raw material for making new plastic goods. In the United States, about 6,600,000 pounds of plastic are recycled annually. That is only around 8% of total plastic waste. But those recycled pellets go on to make more than 100 million new plastic items every year. Shredders and crushers roar as they grind plastic. Conveyor lines move the material through different stages of processing. Recycling plastic saves about 88% of the energy compared to producing new plastic from raw materials. A typical CRT monitor contains almost 3 pounds of lead in its glass. The leaded glass is separated from the monitor's other components. The cathode ray tube is disassembled into individual parts: the screen, the funnel, and the neck. The screen is made of activated glass, while the funnel holds the lead. The glass is cleaned of phosphor and other residues using chemical solutions or mechanical methods. After cleaning, the glass is homogenized. During this stage, you can see giant rotating drums scrubbing paint and resins from the surface. The glass is then sorted by size and sent off for further processing. Thanks to this method, old leaded glass gets a new life while supporting sustainable development. The glass is melted down in special furnaces at high temperatures. Lead is extracted and purified from impurities. This clean lead is used to manufacture new products like batteries, ammunition, or building materials. So yes, it is possible your old monitor might one day help protect the country. Now let us move on to recycling circuit boards. Printed circuit boards are shredded using machines like hammer mills or industrial shredders. This helps extract most of the metal content. The resulting material is usually smaller than 2 inches in size. This shredded material is passed through magnetic separators and air jets to separate metal from non-metal elements. Metals like copper, gold, and silver have unique physical properties that allow for efficient separation. Chemical extraction methods are used to recover the metals. For example, gold and silver are dissolved using acidic solutions. These solutions are then processed to obtain pure metals. Another method involves heating the circuit boards to high temperatures to burn away the non-metal materials and extract the metal content. However, this method can release toxic gases, so it is used with strict safety measures. During chemical recovery, you might see massive tanks filled with acidic solutions where metals are being separated. After extraction, the metals are purified and formed into ingots for manufacturing new goods. Through this process, old circuit boards are reborn as new, useful materials, supporting sustainability and protecting the planet. LED display panels can be recycled for use in making new screens or other electronic components. While the process is complex and not always cost-effective, it is seen as a promising path forward. Some LED monitors contain rare earth elements, which can be extracted and reused. Recycling LED monitors saves up to 70% of the energy compared to making new items from raw materials. What do an old iron and thousands of dollars have in common? That is right, copper. You know, just from one single cord, you can pull out enough copper to make brand new electronics. Every day, tens of thousands of old irons are recycled around the world, taken apart down to the very last screw. But how exactly does this happen? Why can even the sole plate be dangerous? And what is hiding inside the heating element? I am about to show you how dead irons come back to life, from being taken apart to becoming valuable raw materials. Like other electronic appliances, irons are accepted at special electronics collection points. There, they are sorted into categories: those that can be repaired, those that need to be disassembled for parts, and those sent for complete recycling. Worn out or non-working irons are sent to recycling facilities, where the disassembly process begins. When an iron arrives at the disassembly line, specialists wearing protective gloves check it over. Some parts, like the heating elements, can be hazardous due to residual electrical voltage or toxic substances. First, they remove the electrical cord. Its insulation is usually made of synthetic plastic or rubber, and inside there is copper or aluminum wire. Synthetic plastic is durable, flexible, and water-resistant, but when heated or burned, it can release toxic substances, including dioxins, which are harmful to the environment and human health. That is precisely why disposing of it requires special methods. The removed cord is not just set aside. It immediately goes onto a sorting line. First, it is chopped up in a special shredder into pieces about 1 to 2 inches long. This makes it easier to separate the metal from the insulation later on. Next comes the material separation. This is usually done using mechanical or electrostatic sorting methods. What does that mean? What kind of fancy words am I throwing at you here? Look, the copper and aluminum wires are separated and sent off to metallurgical plants for melting. The shredded plastic or rubber goes for recycling, for example, to make new cable insulation or other products. If the insulation contains harmful additives, it might be incinerated in special furnaces equipped with filters or sealed away in a landfill. Separating the copper and aluminum from the shredded electrical cords happens in several stages. So, after the cord is shredded, the pieces are sent to a granulator. This is a special grinding machine that breaks down the pieces of wire into even tinier particles, measuring about 4/100ths to 8/100ths of an inch across. This is how the metal and plastic get separated. Next, the mixture goes into an air separator. This uses a stream of air that lifts the lighter particles up, while the heavier ones fall down. This way, the plastic is separated out even before the main process. If there are any steel components in the wires, like a thin shielding layer or reinforcing fibers, they are removed using a magnetic conveyor belt. But the tricky part is, the little pieces of aluminum wire and copper wire get mixed together, so now they need to be separated. To do this, the metal particles are sent into a metal drum that is charged with high voltage. Copper has different electrical conductivity properties than aluminum, so under the influence of electrostatic forces, they bounce off in different directions and are collected in separate containers. After sorting, the materials are checked again, either by hand or using automated systems. Copper, which is 99% pure, is melted down at a temperature of 1979 degrees Fahrenheit and used for new cables. Aluminum melts at 1220 degrees Fahrenheit and is used to make parts or casings for electronics. This process allows up to 95% of the metals from the cords to be reused, reducing the need to mine new raw materials. Meanwhile, back at the iron, the housing is unscrewed. This could be a plastic or metal shell, depending on the model. A worker wearing gloves firmly secures the device on a table coated with a thin layer of metal shavings, leftovers from previously disassembled appliances. An automated screwdriver mechanism, humming almost silently, moves toward the first screw. The bit fits precisely into the screw head, makes a few quick turns, and the loosened screw flies out into a special container, clinking against the sides. The housing still holds on, as if resisting its fate. But the hands of the technician, seasoned by thousands of these operations, know how to make it give way. A slight pry with a tool under the edge of the housing, and there is a familiar click, like an old machine sighing. The plastic cracks, yields, and then splits into two parts, revealing the device's insides. If the housing is metal, it all happens with different sounds. The metal screws fall heavier. The housing slides across the table with a dull clatter. Sometimes, special cutters have to be used. Sharp blades sink into the thin metal, leaving behind jagged edges that glint under the lights. Finally, the shell is removed, and the device, just a moment ago solid and sealed, seems almost vulnerable. Its insides exposed, ready for the next stage of disassembly. Once the housing is off, the heart of the device is revealed. The circuit board and the heating element connected by a network of thin wires. They are like the veins that powered the appliance in its former life. Tweezers with pointed tips move towards the first contact point. A gentle tug, and the wire pulls away from the board with a faint snap, exposing a tiny copper core. Another tool, resembling a miniature pry bar, slips under the edge of the board. A little pressure, and the board pops out of its place, leaving behind a web of connectors and mounting points. The heating element is the next hurdle. If it is ceramic, it sits inside like a white heart, sometimes coated with a grayish film from countless heating cycles. If it is a nichrome coil, it is wound into a delicate spring, resembling a dried leaf. It is removed carefully to avoid damage, because even the smallest break can complicate further processing. And just like that, with a few more movements, the once unified mechanism falls apart into separate components. The circuit board and heating element are separated, ready for sorting and further processing or disposal. The last part holding its ground is the sole plate. It has absorbed thousands of heating and cooling cycles, signs of use, scratches, and faint traces of scorch marks. It is the sturdiest part of the device, and removing it is not so easy. To get it off, they take a tool similar to a thin pry bar and wedge it between the main body and the sole plate. a barely perceptible push, and you hear a characteristic scraping sound as the metal begins to yield. If the sole plate is aluminum, it bends under pressure, making a slight crunching sound. A ceramic one stays put until it gets a precise tap, after which it separates from the body with a muffled thud. If it is stainless steel, it puts up the most resistance. It often has to be unscrewed by hand or pried off using special levers. Finally, the sole plate is detached. It drops onto the metal table with a dull thud, leaving traces of grime on the worker's fingers. This is the last major piece, and now the appliance is completely disassembled, ready for further sorting and recycling. Imagine a plant spread out over 11 million square feet, where thousands of specialists work every single day to assemble an aircraft made up of more than 4 million parts. Here, in Toulouse, France, giants of the sky are born, from the legendary A380 to the cutting-edge A350. Parts for these aircraft come in from all over the globe. Wings from Britain, the fuselage from Germany, and engines from the United States. This is not just a plant. It is the heart of European aviation and a true marvel of engineering. And now we are going to take a look inside. The Airbus plant in Toulouse covers an area of over 11 million square feet. Now, that is an impressive size for any manufacturing complex, and especially so in the aviation industry. This plant produces not only the A380, but also other aircraft models from the company, like the A350. To produce these technological wonders, Airbus uses more than 2,000 workstations equipped with the very latest technology. This plant is the heart of Airbus aircraft production and a complex logistics hub, where every stage of aircraft manufacturing is its own form of art. The Airbus plant in Toulouse was actually founded way back in 1946 under the name Aerospatiale. Initially, it was a French company specializing in aviation manufacturing, and it laid the groundwork for the future Airbus plant. All the early stages of the plant's operation involved creating aircraft for both military and commercial needs. The Toulouse plant was strategically chosen for its location, which provided convenient access to transportation and logistics routes within France and across Europe. Originally, the plant focused on developing smaller aircraft, but over time, it expanded its capacity and implemented new technologies to produce large passenger aircraft. In 1970, the company Airbus Industry was established, a consortium that brought together 4 major European aviation companies: Aerospatiale from France, Deutsche Airbus from Germany, Construcciones Aeronauticas from Spain, and Air Italia from Italy. From that point on, the history of the Toulouse plant became closely linked with the development of the aviation industry in Europe. This is where the production process for Airbus aircraft began. Aircraft that would become significant competitors to giants like Boeing. Over the following decades, the Toulouse plant expanded multiple times as aircraft production really picked up speed. In the late 1980s and early 1990s, the plant became the main hub for producing aircraft like the Airbus A300, the first certified wide-body aircraft, and the A320, one of the most popular aircraft in the history of civil aviation. Over time, the Toulouse plant became the primary production center for models like the A330, the A340, and the A380, that huge double-decker aircraft that became a symbol of Airbus. In the 2000s, the Toulouse plant underwent major changes and modernization to handle the production of newer models, like the A350, which was introduced to the market in 2013. For this purpose, new assembly halls were built at the plant, including large facilities for assembly and testing, along with new automation systems to boost production efficiency and precision. Manufacturing the Airbus A380 is such a complex and detailed process that it requires innovative methods and technologies for its assembly. Just imagine, each aircraft produced at the plant consists of over 4 million individual parts. These parts are supplied from all around the world, from China to the United States. For example, the main fuselage components come from Germany, the wings from Great Britain, and the tail section from Spain. That is right, The Toulouse plant primarily handles the final assembly of the aircraft. This is standard practice for major aircraft manufacturers. Major engine manufacturers, like General Electric and Pratt & Whitney, supply the powerful jet engines for Airbus aircraft. Additionally, various aviation systems and components arrive from the United States. China is a key supplier of various metal parts, plastic components, and other materials for the aviation industry. Furthermore, Chinese companies provide certain aerodynamic parts. Other parts, including structural elements and fuselage details, are supplied by various European countries, such as Germany, Italy, Spain, and Great Britain. Well-known Canadian companies, like Bombardier, also supply components for different Airbus models, notably for the A220. After being manufactured, these parts are transported to the plant in Toulouse, where they are assembled into a single, complete unit. This often takes several weeks, and the large components are transported using specialized methods, like ships or air transport. The Airbus plant in Toulouse covers an area of 11 million square feet. It is one of the largest aviation manufacturing sites in the world. First, inside the plant's enormous assembly halls, the aircraft fuselage is put together. This is the main body of the aircraft, composed of several large segments that are delivered separately. Each fuselage segment is a major part of the structure, joined together with the others using cranes and specialized assembly machines. A crane lifts the parts, and they are carefully connected using special bolts and welding techniques. This is how the frame structure begins to take shape. Although it is not yet in its final form, once the main fuselage sections are assembled, the wings are brought into separate areas for installation. These wings are heavy, and their installation also involves the use of hydraulic cranes. When the wings are ready, they are attached to the main fuselage structure. Special attention is paid to this stage because the join between the fuselage and the wings is a critically important part that affects the aircraft's aerodynamics and safety. The installation of all the necessary systems, electrical, hydraulic, and avionics, also happens during this phase. Parts are integrated in special clean rooms to prevent any damage or contamination. This is a highly precise process, as all the elements, like cables, pipes, and computer systems, must be correctly positioned within a limited space. Robotic systems are often used at this stage for the precise placement of these elements. Once the aircraft structure is nearly complete and all internal systems are connected, it is time to install the engines. This is another critically important step, as the engines play a significant role in the aircraft's overall stability. Large hydraulic mechanisms and cranes are used to lift the heavy engines and precisely attach them to the aircraft structure. This also demands a high degree of precision and care. As soon as the aircraft is assembled and the engines are in place, it undergoes a series of tests and checks. On the ground, they conduct tests on the braking systems and check the aircraft's response to mechanical stresses. All these operations take place on enormous testing grounds, which allow for trials involving various loads and speeds. At the same time, the functionality of all the aircraft systems is verified. The testing area itself covers about 2 million square feet. After all the tests and adjustments are done, the aircraft moves on to the finishing stage, where it gets painted and the final details are added: window sealants, stripes, logos, and other design elements. Before the paint is applied, the aircraft is thoroughly cleaned to remove any contaminants, grease residues, or dust. Following this, the metal surface is treated to ensure better paint adhesion. An important step is the application of an anti-corrosion coating, which protects the aircraft body from oxidation and other harmful factors. This coating is applied using special sprays or spray guns to create a uniform protective layer. The aircraft is then painted in several layers. Most often, special polyurethane paints are used, which provide a durable, resistant coating. These are applied using rotary atomizers, which allow for even distribution of paint across the entire surface. The aircraft is placed inside a special painting hangar, sort of like a large enclosed area, where the necessary temperature and humidity levels are maintained to ensure proper paint adhesion to the surface and facilitate quick drying. After the base color is applied, a top coat is added, which provides extra protection against atmospheric elements and also gives the aircraft a glossy finish. This layer also adds resistance to ultraviolet rays, preventing the paint from fading in the sun. After painting, the aircraft are inspected for any defects. If any cracks or bubbles appear in the paint, they have to be corrected. In the final stage, airline logos or special liveries are applied to the aircraft. This might involve not just applying paint, but also installing special decals or applying a protective film to the surface. This process can take up to several weeks for a single aircraft, depending on the size and complexity of the livery. In total, painting a complete Airbus aircraft requires about 3,300 pounds of paint. The process of installing the cockpit is one of the most complex and precise operations. The aircraft cockpit, especially in models like the A350 or A380, contains hundreds of different sensors, control systems, displays, and other technical elements that must be precisely configured. Altogether, a cockpit can contain up to 5,000 different parts. Interestingly, the assembly of the cockpit takes place separately from the main aircraft body. This is done in special workshops where the cockpit is fully equipped before being transported for final integration into the aircraft. The entire cockpit installation process takes several days and demands the highest level of precision, because any malfunction in the control or navigation systems could lead to serious problems during the aircraft's operation. Another crucial aspect is the integration of avionics, which are the aircraft's electronic control systems. These systems allow pilots to monitor flight parameters, engine status, the situation in the sky, and perform other critically important functions. Installing the avionics takes anywhere from several days to several weeks, depending on the complexity and type of the aircraft. More than 10,000 people are involved in the aircraft assembly process, including engineers, technicians, testers, and other specialists. The production cost for a single A380 aircraft is around $445 million United States dollars, making this project one of the most expensive in the world of aviation. Just for the development of new technologies and the improvement of automation processes, Airbus spends millions of dollars every year. Have you ever seen a ship that does not touch the water? Now, imagine that such a vessel not only exists, but can also carry tens of tons of cargo and accelerate up to 250 miles per hour. Meet the Hovercraft landing craft, a unique combat vehicle that glides above water, land, sand, and even ice. Its engines are just like those in fighter jets, and its maneuverability lets it drift on waves. But how much does this technology cost? How do they build it? And why are even seagulls afraid of these machines? Let's find out. The idea of using an air cushion came from the British engineer Christopher Cockerell in the 1950s. He experimented with airflows using tin cans and a hairdryer, ultimately creating the concept of a vehicle that could glide over any surface. In 1959, the world's first real hovercraft was launched. Later, this technology found its way into military use, specifically in LCAC-type landing crafts developed in the United States during the 1970s. So, Cockerell invented it, but the military refined the idea into its modern form. Let's move forward. Or maybe sail ahead. Manufacturing hovercraft landing crafts involves several stages. Initially, design bureaus create drawings and digital models of the craft. The design process depends on whether it's a new project or an upgrade of an existing one. Creating a completely new hovercraft takes from 6 to 12 years. Imagine that. Preliminary design and concept stages last from 1 to 3 years. Developing drawings and digital models adds another 2 to 5 years. Building and testing the prototype takes an additional 3 to 5 years. Finally, we get a ready-to-use craft. If we're talking about upgrading an existing design, the process takes half the time. Analysis and adaptation of drawings take from half a year to 1 year. Updating digital models takes only 1 or 2 years. Building and testing the updated version takes 2 to 3 years. The newest American hovercraft, called the Ship-to-Shore Connector, replacing the LCAC, began development in the 2000s. The first test models were ready in 2012 and 2014, but full-scale production started only in the 2020s. The process is lengthy because these crafts must be reliable, fast, and suitable for challenging operational conditions. After drawings and digital models are developed, suppliers of materials and components are selected. The military announces tenders, where companies compete for contracts. Manufacturers must pass certification and prove their materials withstand extreme conditions. Some components are produced exclusively domestically for national security. Thus, the process is complex but critically important. If even one component fails, the entire mission can be jeopardized. The craft's frame is assembled at shipbuilding yards. These massive industrial complexes are usually located on coastlines or near large rivers. They cover areas from dozens to hundreds of acres, since multiple vessels must be built simultaneously, with space for storing materials and heavy equipment. There are huge covered or open areas where ship hulls are assembled. These areas can be from 500 to 1,500 feet long to accommodate large structures. In metalworking workshops, aluminum alloys for the LCAC hull are cut, welded, and shaped using robotic machines and laser cutting. Shipyards also include dry dock basins, enormous artificial pools, where finished crafts are tested before launching. Massive gantry cranes with lifting capacities from 100 to 1,100 tons move large sections of hovercrafts. Additionally, there are areas for installing gas turbine engines, radar, and navigation systems, as well as logistics yards, where incoming materials and components from suppliers are stored. One of the largest such shipyards in the United States has been building military vessels for more than 100 years. The frame assembly of a hovercraft landing craft is constructed mainly from aluminum alloys, using welding and assembly methods different from traditional shipbuilding. Aluminum sheets and profiles are supplied as ready-made blanks. Robotic machines cut out parts according to computer-generated drawings. Sections for the future frame are prepared in special workshops. The LCAC structure is not assembled entirely at once, but built from large modules. Each module, for example, the bow, stern, and side sections, is assembled separately. Rivets and aluminum welding ensure durability. The frame consists of a keel beam running the length of the craft and transverse ribs providing rigidity. Aluminum rivets and specialized adhesive mixtures are used to connect sections, reducing weight. Large modules are lifted by powerful cranes and connected precisely using laser positioning to avoid errors. At the brightly illuminated shipyard, a giant module of the future craft rises into the air. A heavy gantry crane, weighing hundreds of tons, slowly lifts the aluminum section, gleaming in the sun like the shell of a marine predator. Metal cables are stretched tight like strings, while workers in protective helmets and vests carefully monitor every movement. The enormous part floats mid-air, gently swaying in the breeze. A crane operator, sitting high above the yard, maneuvers this colossus with extreme precision. Engineers below signal instructions, guiding the module to its exact position. When the section slowly settles into place, there's a dull metallic thud. Thousands of pounds of aluminum collide with the frame. Immediately, fastening begins. Workers tighten bolts, welding machines ignite with bright blue flames, and sparks scatter from beneath electrodes. The air fills with the scent of hot metal as the craft gradually takes shape, becoming a formidable combat machine. Engineers inspect structural integrity and tightness. Attachment points for the hovercraft skirt are installed on the frame. This system must be completely airtight to maintain LCAC stability during movement. The completed frame undergoes load and vibration tests. After passing successfully, engines, propellers, and electronics are installed. Now begins one of the most critical stages. The shipyard hums with crane motors, gently transporting massive gas turbine engines, the heart of the future craft. Workers dressed in protective suits and masks precisely position them in compartments, where every millimeter counts. Simultaneously, technicians attach enormous propellers, blades made from robust composite materials, which will later propel air with thousands of horsepower. When blades rotate for the first time, air waves ripple through the air, causing fabric on work uniforms to tremble. Inside, engineers connect cables, sensors, and onboard computers, carefully inspecting every chip, screen, and controller, as navigation, communication, and automated control depend on these systems. Once everything is ready, the moment of truth arrives. Pressing the first launch button, the massive frame shudders, turbines roar to life, and the first stream of hot air bursts from exhaust channels. The LCAC is ready for its first water test. A single modern LCAC costs from $50 to $75 million, depending on modifications. Operating costs are high due to gas turbine engines and demanding maintenance. Maintenance can occur at shipyards or specialized bases. Gas turbine engines require frequent service due to limited lifespans and costly repairs. The Hovercraft skirt wears from contact with water, sand, and stones. Propellers and air systems require repairs as they operate continuously at high speeds. The United States is the leading producer of the new ship-to-shore connector crafts, replacing older LCACs. Great Britain builds similar crafts for civilian and military markets. Who uses them, you might ask? The United States Navy is the largest operator, possessing about 70 LCACs and acquiring new models. Japan uses LCACs for defense and humanitarian missions. Potential customers include NATO countries and nations expanding amphibious forces, like India and South Korea. Currently, LCACs are being upgraded to SSC, quieter, faster, and more efficient crafts. Demand is rising due to threats in the Pacific region and the need for rapid troop transport. Additionally, LCACs can drift. With the air cushion, they lack typical friction with water or land, allowing them to slide sideways, sharply change direction, and even pivot almost in place, making them exceptionally agile but challenging to control. LCACs use the same gas turbine engines as military aircraft, specifically the General Electric LM2500. Similar engines power F/A-18 Hornet fighters. Essentially, LCACs are aircraft that never leave the surface. Unlike conventional ships, they can move onto shore, cross sandy dunes, swamps, and even ice, providing advantages for landing troops in difficult locations. However, LCACs are among the loudest vessels in naval forces. Their noise can be heard hundreds of feet away, making them unsuitable for stealth missions. During operation, LCACs create powerful vortices, capable of literally blowing away seagulls and other marine birds, often making it impossible for them to remain airborne.